Greetings and welcome to lecture number 15 on the course Introduction to Fourier Analysis. In the previous set of lecture notes, we developed the theory of the Fourier transform for L1 and L2 functions. For functions in either one of these spaces, we were able to define the Fourier transform as a complex-valued function f hat on Rd, which satisfies the so-called duality formula for all Schwarz functions phi. Namely, the integral of f times hat phi equals the integral of hat f times phi. If f is an L1 function, this was easily accomplished by the pointwise formula f hat of xi equals the integral of fx times e to the power minus 2 pi I xi.x dx, and the resulting function f hat was an element of L infinity. For f in L2, defining the Fourier transform was a little trickier. The Fourier transform f hat was defined as the image of the linear map calligraphic f, namely the unique bounded extension of the pointwise Fourier transform map from the space of Schwarz functions to L2. In particular, the Fourier transform of an L2 function was again an L2 function, even with the same norm. This fact was known as the Plancherel identity. On this lecture, we move beyond the spaces L1 and L2. We would like to define the Fourier transform for all LP functions, but it turns out that there is a surprising conceptual difference between the cases where p is between 1 and 2 and the case where p exceeds 2. The case of the exponent p between 1 and 2 does not require substantially new ideas, so we begin there. In fact, this case follows pretty much the same pattern as the case p equals 2. The idea is again that the Fourier transform has already been defined on the dense subspace of Schwarz functions. All we need to do is to check that the Fourier transform map is bounded in a suitable way on this dense subspace, and then we can extend the definition in a unique bounded manner to all LP functions. Theorem 4.1 tells more precisely in which way the Fourier transform is bounded on LP. Let p be an exponent between 1 and 2, and let q be the dual exponent of p, namely the unique number satisfying 1 over p plus 1 over q equals 1. Let x be the space LP and let y be the space LQ. Finally, let x0 be the space of Schwarz functions equipped with the LP norm. This space is dense in X. Then the Fourier transform map calligraphic f0, defined on the space x0 and taking values in y, is bounded, in fact with constant 1. The LQ norm of the Fourier transform of any Schwarz function is bounded by the LP norm of the Schwarz function. This inequality is often known as the Hausdorff-Young inequality. It is a generalization of the cases p equals 1 and p equals 2, which we have seen in previous lectures. We will prove Theorem 4.1 in a moment, but let us first use it to define the Fourier transform of LP functions, when p is between 1 and 2. Exactly as in the case p equals 2, the bounded linear extension theorem gives us a unique bounded linear map calligraphic f between the spaces LP and LQ, whose restriction to the space x0 of Schwarz functions coincides with the usual pointwise Fourier transform. Then, as we state in definition 4.2, if f is an LP function with p between 1 and 2, the image of f under the extension calligraphic f is by definition the Fourier transform of f. Thus, the Fourier transform of an LP function is by definition an element of LQ, whenever the exponent p lies between 1 and 2. There is no conceptual difference to the case p equals 2. Also, as in the case p equals 2, it is easy to check that the Fourier transform of an LP function is a weak Fourier transform. This is recorded in proposition 4.3. If f is an LP function and p is between 1 and 2, then the integral of f times hat phi equals the integral of hat f times phi for all Schwarz functions phi. We leave the proof as an exercise. It goes in the same way as the case p equals 2, which was proposition 3.16. What remains to be done is to prove Theorem 4.1, namely the Hausdorff-Young inequality. The idea is that we already know the inequality for the cases p equals 1 and p equals 2. In order to prove it for the intermediate exponents p between 1 and 2, we use an abstract interpolation result known as the Riis-Torin interpolation theorem. This theorem states the following. Let p1, p2, q1 and q2 be exponents between 1 and infinity. Let T be a linear map, which is initially defined on the sum space LP1 plus LP2 and takes values in the sum space LQ1 plus LQ2. For our application, you should think that P1 is 1, P2 is 2, Q1 is infinity, and Q2 is again 2. And the map T is the Fourier transform map. Then assume that the map T is bounded from both LP1 to LQ1 and from LP2 to LQ2 with constants C1 and C2. Then the conclusion of the theorem is that T is also bounded between all possible intermediate spaces. More precisely, if theta is a parameter on the interval from 0 to 1, then T is bounded from LP theta to LQ theta, where the exponents p theta and q theta are defined in a slightly awkward way. Namely, 1 over p theta equals 1 minus theta over p plus theta over p2, and similarly 1 over q theta equals 1 minus theta over q1 plus theta over q2. The Riis-Torin theorem also provides a quantitative estimate on the boundedness constant between LP theta and LQ theta in terms of the constants C1 and C2. The boundedness constant is at most C1 to the power 1 minus theta times C2 to the power theta. The proof of the Riis-Torin theorem is not difficult, but it relies on some complex analysis, and we will skip the proof. For the details, see Theorem 1.3.4 in the book Classical Fourier Analysis by Lukas Grafakos. Now, taking the Riis-Torin interpolation theorem for granted, let us complete the proof of Theorem 4.1. We already know that the Fourier transform map is bounded from L1 to L infinity and L2 to L2. So, as we mentioned, we want to apply the Riis-Torin theorem with exponents p1 equals 1, q1 equals infinity, and both p2 and q2 equal to 2. Then the conclusion of the Riis-Torin theorem is that the Fourier transform map is also bounded from LP theta to LQ theta for all parameters theta in the interval from 0 to 1. Finally, it takes a few lines of elementary school calculations to check that this statement is equivalent to what we claimed in Theorem 4.1, namely that the Fourier transform map is bounded from LP to LQ whenever p lies between 1 and 2, and q is the dual exponent of p. We also claimed in Theorem 4.1 that the constant of boundedness of the Fourier transform map between LP and LQ is equal to 1. This follows from the same argument. To see this, check out the estimates for the boundedness constant that we obtained from the Riis-Torin theorem. This completes the proof of Theorem 4.1. As we have already mentioned a few times, the same idea for defining the Fourier transform does not work when the exponent p exceeds 2. In fact, for such an exponent p, there is no exponent q between 1 and infinity, such that the LQ norm of the Fourier transform of phi would always be bounded by a constant times the LP norm of phi, when phi is a Schwarz function. We will see this in the exercises. So, we need to find a new idea for defining the Fourier transform in this range of exponents, and this is where the space of tempered distributions will be needed. These will be defined and studied on the next lecture. This completes lecture number 15 on the course Introduction to Fourier Analysis. Goodbye for now.